Let's get started. I want to continue my discussion on channel capacity using this note that I started last time. I talked about channel capacity, Carver and Thomas, chapter 7 of the second edition, chapter 8 for the first edition. It also described some of the physical channels. And when you take a look at the Hamming code, my Hamming code note, I'll also talk about two physical channels. One is cell phone channels, the other one is internet. And here I talk about different forms of channel capacity. First kind is log of size of the message set. Okay, so when you have 8 messages to send over a channel, then log 2 of size 8, size which is 8, then that is 3 bits. So that's the capacity of the messages set. If these messages are sent over a channel with almost no error, this capacity can be achieved. And T is the time required to transmit a message in the set. Then you divide this capacity 1 by the time for you to transmit a message in the set, then it becomes bits per second capacity. So this becomes more physical. Right? And another capacity definition is to use the notion of one channel use, a single channel use. For example, a physical channel can be used once. That means you have to occupy the transmission channel for a given time and a given frequency range. So you have to use this. You have to use this frequency and time, channel in order to send your message. In such a case, we can define a single use of time and frequency of the physical channel. Then we can say that is a single channel use. If then it requires for you to use these physical channels n times, and then in n times you send a message, then basically the capacity can be defined this way as the size of the message set that you can send. But in order to send a single message in the message set, you have to use n channel uses. You have to make n channel uses. Then the capacity per a single channel use can be defined as bits per channel use. So that's the bits per channel use. Capacity is the number of bits that can be transferred over a given channel with almost no error. So this a given channel has a variety of, as I have said right here, of different definitions. Okay. So that's channel capacity. And here I use the term with almost no error. And here is the explanation. Why almost no error? It has to do with the law of large numbers that we have discussed in previous lectures. Recall the convergence in probability. Recall the surface hardening argument. As the dimension increases, the probability of the set of samples on which the discrepancy between the converging random variable and to what it is converging is getting smaller and smaller. So that is the meaning of the convergence in probability. As the dimension is enlarged, the magic occurs, and the error gets smaller and smaller. That's what we will see in the proofs of channel capacity theorem. Okay, so discrete channel I talk about here. So here from a message set, you select a message, and then in order to send this message, you need to do the encoding. When you do the encoding, you have a set of symbols that interfaces this channel. This channel is given by input X, output Y, and then probability distribution. And then you received these symbols of written as Y's, and superscript here means you are doing a vector transmission and a vector reception. And when we use this channel in order to send a vector of length n, then you have to use this channel n times. And if the channel is memoryless, then basically the vector input, vector output, the probability distribution of that is a product of each input output probability distribution. So this is the case that this distribution is IID for each channel used, then it becomes this. And as we have seen in the Hamming code notes, where I described cell phone channels, basically we can transform the physical channel into the discrete channel, as we have seen, as we have described in, as we describes in this note. So here discrete means that these inputs and outputs can be modeled as discrete random variables. Sometimes, I mean, later on in our lectures, the output Y can be modeled as continuous random variables, and that will come later on when the output is continuous random variable. But this argument, I mean, this structure that we see here doesn't change much. So we, for the moment, we assume that inputs and outputs are all discrete random variables. And then once you received the word symbols of Y's from the channel, then you give this as an input to the decoder, and decoder does the decoding operation. Basically, it determines, it aims to determine what was the message that was sent at the transmitter. So we call W prime, and the probability of error means that it means the event that W is not equal to W prime. So you can read about this if you know if you have taken the digital communications course in your undergraduate years, then you can understand this, but I will not talk too much about this one for now. And here, information channel capacity is defined. So information channel capacity is based on mutual information and based on this description right here. So information channel capacity, C, is defined to be maximum of mutual information, where the maximum is taken over PX. Okay, so the input distribution, input symbol distribution. So maximum is taken over all possible input distribution P of X. Okay, so this is well defined mathematically. And as you have recalled in your midterm exam or my previous lectures before the midterm, basically mutual information given a channel where P y given X is fixed is a concave function of Px. So this maximum is well defined. So you can find a unique you can find the maximum. You can find the maximum C. You can do the maximization and find C. Okay, and this is mathematical description, and we can also talk about operational channel capacity, and then we can compare this information channel capacity with the operational channel capacity. So operational channel capacity is more practical, way, basically using vector processing. So this is the highest rate in bits per channel use at which the information can be sent with an arbitrary small probability of error in practice. Shannon proved that this operational channel capacity is equal to the information channel capacity. So here I talk a little more about operational channel capacity. That is the capacity of a code in practice. So what is a code in practice? So a code in practice, as you have seen the example of Hamming codes, is in the following form. There is a code book. So you use a code book. A code book is a collection of code words. Okay, and the size of the code book is 2 to the power of NR, where R, bits per channel use, is the rate of the code. Okay, so for the example of Hamming code, 7/4 Hamming codes, what is R? In order to see that, basically the code has length 7, right? So you have to use the channels 7 times, and while you are using the same channels 7 times, you are sending how many bits? Basically, you are sending 4 bits. So the Hamming code case, the rate R is 4/7. So you are sending 4 bits, 4 message bits or information bits per single channel use. Per single vector channel use. So in terms of per channal use, you have to divide it by 7. So the rate of the 7/4 Hamming code is 4/7. So the size of the code book is 2 to the power of NR. That is the rate of the code book. And this the rate of the code, the size of the code is where R is the rate of the code, and this is to mean there are 2 to the power of NR code words. Okay, so in the case of a Hamming coder again, N is 7, rate is 4/7, so there are 2 to the power of 4 code words. Okay, so for example, suppose R is, but this one is, I'm using another one now. So for example, suppose R is equal to 0.5 and N is equal to 6, then there are 8 binary code words of length 6. Okay, why binary? Because this is base 2. Number 4, I talk about encoding. Encoding is a function from a set of messages to a set of code words, which is code book. This function maps a message from the message set to a code word in the code book. Suppose the same example given in 3, which is this, N is equal to 6, rate is equal to 0.5. There are 2 to the power of 3, which is 8 messages. So they can be enumerated by binary strings such as 0000001 and all the way up to 111 without loss of generality. And then each message is mapped to a code word of length 6 in the code book. So the term a single channel use is to mean that the channel is used once. And in order to send a length 6 vector like this, then you have to use the channel 6 times. And then you obtain received vector. If the channel use is independent and identical, which is memoryless, then the vector channel can be given as product of each marginal conditional probabilities. Then once you got this received vector, then you do the decoding at the receiver. So decoding is a function from the set of outputs of the channel to the set of messages. First, it maps an output vector to an input vector. So basically, it is doing the demapping that was done at the transmitter. Okay, so this is a code word, right? Beta B, right? And then from a code word, you do the demapping again to find the messages, corresponding messages. To find the corresponding messaging. And once you found the corresponding message, then you know information bits. That's the end of decoding. And then the an error event occurs when the transmitted message, which is one of these, and the decoded messages, when the transmitted message and the decoded message are not the same, then you have a decoding error. And as the channel capacity theorem says, the operational capacity is the same as the information theoretic capacity. That means as we increase the block length, which is n, then the probability of error you can make converges to 0. So that's the big picture view of channel capacity theorem. And then how do you prove it? Basically, based on convergence in probability. We will talk about that later on.